I don't think you need to. Waiting for precisely 10:30. Is everybody in from back there? All right, I'll wait a few minutes more.
You're making it harder for the editor.
Yeah, well.
I mean, they got to now chop off a bunch of time.
Yes, they do. But that actually isn't my fault. I wasn't the one that started the recording. Do we have everyone, Johnny? Should I just start then, even though we're early? All right. So for our next talk, we're going to hear a bit about the toolkit that made all of this possible, that brought us all together in this room this year, the Einstein Toolkit. And this is a traditional talk which confirm my speaking language. Okay. Well, this is a traditional talk which we have at most of these things to get the new students acquainted with the toolkit and how it came to be and why it works the way it does. And later on this afternoon, I will be giving a tutorial on how to actually use it. So to set that stage, here is Yosef Zlochower from RIT.
Well, thank you. And well, to start off, it's my job here to give you an introduction to the Einstein Toolkit. I would like to thank Roland and Steve and Peter and Frank Loeffler for providing me the slides that I'm going to be using to give this presentation. As Stephen says, this is a traditional talk given at every Einstein Toolkit school. Okay, so what is the Einstein Toolkit? Well, it's a collection of scientific software that's used generally to simulate general relativistic astrophysical systems. The toolkit itself is freely available and open source, and it's been supported over many years by the National Science Foundation in the US. You can see here a list of some of the recent grants, but these are just recent grants. In fact, I believe this is only 2, though split over several institutions. But it's been continuously funded since I guess, the mid-2000s. And there are currently at least 456 members in 319 sites across at least 49 countries. There has been many publications that have used the Einstein Toolkit, and at least at least 58 theses, probably a lot more. If you do, if you do go on to use the Einstein Toolkit in your PhD work or your master's work, it'd be nice to let us know so we can update those numbers. It's been used in the spec benchmark. It's received prizes. It showed up in a science fiction story, and importantly for everybody here, I would think, is that it's regularly tested, and there's many different ways in which a new user or an existing user can get support. There's a mailing list, there's a weekly meeting, and we'll talk a little bit more about those. Okay, so what kind of science is currently done with the toolkit? So, as we saw in the previous talk, binary black hole mergers are routinely done with the Einstein Toolkit. Also neutron star mergers, supernova calculation, accretion simulation, and boson star and also simulations of cosmic censorship and black holes with hair, um, and modified theories of gravity, and many others. The latest release is codenamed the Kruskal release. It's named after Martin Kruskal, um, uh, and it was released at the end of May. And you can see the release managers, and I want to thank them. And there are many new features in the toolkit. There's a new Cauchy characteristic extraction module, which we'll hear about later today. There is a cosmological spacetime initial data solver. There's also been some updates that will be more relevant to the users of the toolkit rather than just introduction, is that there are new finite differencing algorithms. There's also a new driver, Carpet X, and we'll hear about later on in the week some really interesting things that could be done with this new driver. Okay, the Einstein Toolkit is a community effort, and the reason for the community effort has to do with just the nature of the computational challenges associated with running with actually producing code which can solve these problems. And one of the issues that when you have to think about when writing a modern code is how to run on modern hardware. As modern hardware starts, we've left the era where there was basically just a single CPU that was dominant, and you just had to write code for that. And now we have both CPUs and we have various types of accelerators, and we need a code which can actually run on all these different platforms. And if you learn more about these platforms, you'll see that the actual type of coding required is quite a bit different as you go from platform to platform. This is an image showing the Frontier cluster. It is the largest supercomputer available for general scientific research, and this is a GPU-based cluster. So if you want to get access, if you want to run on this cluster, you're going to have to be running on, you're going to have a GPU-enabled code. Okay. So again, computational challenges. So what makes it hard? So first of all, we have, as I was saying, we have new hardware coming online, and that new hardware, each type of new hardware requires a different type of specialization of your code. So for example, on a typical CPU code, you have to be, for example, careful about cache and cache alignment and making the most of getting enough data onto your CPU fast enough. And then there's also the vectorization. So a modern CPU can do multiple instructions, a single instruction on multiple data using vectorization. So you want to have your code which can exploit that. Then there are the accelerators. And for example, and when we're talking about accelerators, really, I mean, the thing that we want to talk about here are GPUs. Okay, so you want to be able to make use of GPUs. Now, also, modern processors tend to have a lot of computing cores per CPU. So you want to make sure that your code scales effectively to many cores. But of course, you also want it to scale to many nodes, to many compute nodes. And so that's going to require, again, each one of those is going to require optimization. And then, of course, you have to worry about the algorithms themselves. Whoops. Okay. Now, basically, this becomes a major challenge because the efficient use of on all this different type of hardware is basically a complex process, and it's very difficult to actually do, and requires expertise in computer science. Also, you can't just do naive programming. You have to think really carefully about the data and how it's stored. And then also, your codes are necessarily incredibly complex. And if they're going to be incredibly complex, they have to be tested. And so we need a way of modularizing, you need a way of modularizing the code, and so you can test those modules. And basically, you need to be careful about, all this has to be careful. You have to keep thinking carefully about how you're going to actually bring all these codes together in order to actually ensure that they actually run both effectively and correctly on different hardware. Okay, so basically the way that the fundamental way that Einstein Toolkit deals with parallelization is through the use of ghost zones. So we can imagine we have a grid, and we want to take that grid and we want to distribute it onto different computers. Well, if we were to do that, what we notice is if we try to do finite differencing, when we got to the boundary of the grid on one processor, we'd be missing information. We would want to take a derivative, so let's say we would need at least a data point over, but we can't because that data point is actually belongs to another processor. And the same thing would happen, in this case, for processor one. So what we do is we use something called ghost zones. We basically add an extra point to each processor. I shouldn't say an extra point, but depending on the width of your stencil, it could be an extra anywhere from, extra point to an extra, order 10 points. And basically, these points are going to be updated by another processor. But that update is communicated so that when processor 0, for example, needs to do an update, it's going to have correct information in what's in this ghost region, and then it can update this point here. And then processor, in this case, processor 1 has an extra point as well. And again, it can do its update. And then this updated point can be copied over. And similarly, this updated point can be copied over. And that's how you fill in the ghost zones. Okay, and then here's the domain decomposition. And basically, we have our domain. We first kind of split it up logically into different subdomains. Then we distribute the subdomains onto different MPI processes. And we have to add to each subdomain these ghost zones. And basically, the Einstein Toolkit will take care of the communicating the ghost information between the different processors. So you can write a code which basically looks like it updates a single grid, and it's just running independently on a bunch of different processors. Okay, but you can go beyond that. It turns out that the most effective grid that you can set up for a binary black hole simulation is not a Cartesian grid everywhere. Cartesian grids are really good for resolving things like the dynamics near a black hole. And so we have here kind of a sketch of what a grid might look like. We imagine we have two black holes roughly at the centers of these two refined blocks here. And as we move away from the black hole, well, we need less resolution. And so we could imagine immersing this high resolution block inside a larger, lower resolution block, or let's call it level. And then those might be immersed in even coarser levels, and so on. And again, Einstein Toolkit will be able to handle that. But as you start to move very far away from the black hole, something else happens. You need resolution in particular directions. Okay, and therefore Cartesian coordinates are not the best way to do this. And so what we have is a different, a multi-block structure where we have these basically spherical coordinates basically mapped onto a set of in this case, touching blocks, coordinate blocks. And again, the Einstein Toolkit with the code llama can actually handle this and actually provide correct boundary conditions so that all the different types of blocks that you see here can communicate effectively. And again, you have your codes which are running on this can be relatively simple, but make use of this extremely complicated infrastructure. Okay. Other things you got to be worried about is, well, it's relatively easy to write code that gets something done. It's much harder to write code that actually gets something done in the most efficient way. And so there are tools that we have in the toolkit to actually basically take an algorithm that you have, in this case, in a high level language, where we basically can express tensorial. You basically express what you want in terms of tensorial notation of some kind, and the code will then produce. These codes will then produce actual source codes, which can make use of various hardware. In this case, for example, vectorization. Okay. We typically use OpenMP to scale to many cores. At least that's required when you have large numbers of MPI processes. Scaling to many nodes is done with MPI, and the actual code that actually handles that is going to be a code called, which you'll hear about more, Carpet, which is part of the core part of the Einstein Toolkit, and Carpet X, which is its successor, which is going to be kind of the next generation Einstein Toolkit driver. Okay, and then the actual adaptive mesh refinement, which is where you have these blocks of different refinement levels sitting inside each other. That's handled through the driver as well. So the driver handles MPI, but it also handles mesh refinement. And again, this is done with Carpet and later on with Carpet X. Mole, in this case that's mentioned here, that's a particular code using Carpet, which actually does the time integration for you. Okay, and then got to make use of GPUs. If you want to make use of GPUs with the Einstein Toolkit, you should be looking towards using the Carpet X code. Okay, and then there are some potential other challenges that we can imagine, but I don't know if there's any codes which actually make use of FPGAs or these other types of accelerators. Okay. So there are other challenges we have to worry about. We're now imagining very large simulations. So that means that we have a lot of data and we have to effectively get the data onto disk. So we need an efficient way of inputting and outputting data. That efficiency is both quickly to get the data onto disk or from the disk, but also efficiency in terms of storing the data. You know, you could imagine writing data entirely in ASCII. Well, if you want to have high precision data entirely in ASCII, you're going to be very, very wasteful. Just think about, you know, a single double precision number can be stored in 8 bytes or it can be stored in, I don't know, 20 bytes, 30 bytes, depending on whether or not you want to store it in binary or in ASCII format. To get it, so in Carpet, the key method for efficient I/O is use of a library called HDF5, which is a nice library. It stores data in a binary format, and it stores data in a system agnostic format. So you can basically write data from one type of system and read it on another type of system, and it'll handle behind the scenes. It'll handle all the issues associated with the fact that the two different systems might actually have two different representations for the same data. Okay. Associated with input-output is also checkpoint and restart. So if you're doing a simulation, you know, the simulation might take days to weeks to months to run. Well, on a typical computer cluster, you can run for, 12 hours, maybe 48 hours at a time. So how do you do a week-long or a month-long simulation? Well, you break it up into 12-hour chunks or 48-hour chunks. And so you need to be able to start a simulation, save its state, and then restart it so that the simulation could continue the next time around. And in Carpet, this checkpoint and restart are all handled using HDF5 files. Now, if we're talking about a simulation, typically we have a code in the Einstein Toolkit isn't designed to do one particular simulations. It's designed to do any number of related simulations. And you fine-tune the simulation you're actually doing by essentially setting up what's called a parameter file. So it's a file which is going to describe your simulation in detail, and you need a way of actually reading that data, that file, and actually setting things up correctly. So there's a sophisticated parser which will actually read the parameter file that you have, and you'll see examples of this, I guess, later today, and actually translate that into actually adjusting variables inside the code itself. Other things, you need to be able to visualize your data. So there's a few different, if you're doing a three-dimensional simulation, let's say of a binary neutron star merger, you're going to have some way of actually looking at what the hydrodynamics is actually doing. And so probably the best way of doing that is to actually be able to visualize the three-dimensional data to interpret what's actually happening. And so there are, again, tools both within the toolkit and tools outside the toolkit, which can use the Einstein data generated from the Einstein Toolkit to visualize. And again, you're going to need to probably do visualization may not be sufficient. You're going to need to do some kind of analysis. And analysis might be anything from extracting gravitational waveforms to measuring the accretion rate of an accretion, of accretion onto a black hole, and many other things. Okay. Other things maybe you might need to do is something called steering. That is, during a run, you might have to change particular parameters. For example, you might have a simulation, a binary neutron star simulation, where the number of well, neutron stars are basically much larger than black holes in terms of area. But if you have a binary neutron star which merges and then the neutron star itself collapses to a black hole, suddenly you go from a large object to a much smaller object. So you're going to need to basically now increase your resolution very rapidly. And so in that case, you would want to steer parameters associated with your grid to basically add all the refinement levels you would need to resolve the black hole, whereas before you had some kind of large hypermassive neutron star. So the Einstein Toolkit is fundamentally a collaborative tool, and in collaborations there are challenges that you have to deal with. Okay, so first thing is, kind of the nature of the collaboration. You have a bunch of different groups who are trying to solve related problems, maybe not identical problems, but related problems. And so basically, there's going to be these methods which are going to essentially, which are going to be common to all these problems. And so wouldn't it be really great if we can take all these different groups and say, you all need this common code base. So let's work on a common code base, and then we can all do it for these. Then we can all apply the code base for our projects. And so that would imply, that basically means we want to build a community around this software development, which is really what the Einstein Toolkit is about. And of course, community requires tools to actually engage. And so the toolkit, as kind of mentioned before, the toolkit engages with the Einstein Toolkit engages with its community through weekly telephone conferences, through a mailing list, through wikis and through bug tracking, and basically everything the Einstein Toolkit does is in some sense in the public, and anybody can see what's going on and can participate. And here's some of the collaborative tools that we use. Okay. So one of the other things you might wonder about is what about, we've been talking in a previous talk, we saw, that there's a lot of different groups trying to produce gravitational waveforms. Okay, so we have competition as well. So we have collaboration and competition. Okay, so basically, what do we do for that? Well, basically, the Einstein Toolkit essentially enables people to do the science. And yeah, different groups might be wanting to do very similar science, and that's perfectly fine. In fact, that's actually beneficial. So the toolkit itself provides the means for doing the sciences. Now it's up to different groups to actually do the science. Okay. Other things we need to worry about is code quality and making sure that if we're going to encourage a bunch of different people to come in and say, do your science with our code, that the code itself is producing the correct results. Okay. Okay. And also, basically, we're going to deal with issues of how do we actually make sure that we can communicate effectively not necessarily between different groups, but as somebody who's writing a code in one framework is contributing to the toolkit, how can other people make use of the code? And again, it's through this through basically setting an interface where people can actually effectively communicate data across. Okay, there are many different tools that we're going to use, but basically, the fundamental languages that are supported by the toolkit, and also there's basically different. So I'm actually going to skip that one. Okay. Sticking point when it comes to academia, if I contribute to a project, and other people make use of the project, that might be great in principle, but but the typical way that we handle this in academia is through giving credits. By credit, I mean, essentially citations. And so, so how do we deal with that within the toolkit? So effectively, what we do, what there is essentially, if you do contribute code to the Einstein Toolkit, you can request citations, and I'll talk about this a little bit later on. There is a list of requested citations which are linked to on the Einstein Toolkit webpage. Okay. This slide is just showing you, where some of the collaborators actually who support the toolkit and who use the toolkit are located. And basically, this list is this list is definitely incomplete because you saw on the other slide, there is actually 50 countries involved. And so the collaboration itself is widespread. Okay, so now that I'm kind of motivated why we need what the point of the toolkit is and why it's needed, what are its goals? So the Einstein Toolkit, there are many ways that one could set up a collaboration. The Einstein Toolkit is set up in this community-driven way, where basically the work that's done on the toolkit is more or less decided at the researcher's level. So it's decided, it's not typically done top down. There's no, there's not leader of the toolkit who says do this and things are done. It's more along the lines of the community says we need these, we have these features, we need these features, we want to incorporate these features, and let's work on it. Okay. So the main components of the Einstein Toolkit are, first thing is kind of the underlying the Einstein Toolkit itself is the Cactus infrastructure. And Cactus is a code which dates back to, was first developed at the Albert Einstein Institute in Germany. And it's kind of the glue which holds all the different components of the Einstein Toolkit together. There's also tools like Simulation Factory. Simulation Factory is a tool which it's designed to, once you have a simulation you want to run, there's a whole other level of complexity associated with actually just running the simulation. So keeping effectively, queuing it up, of getting the, we've talked about how you need to have multiple jobs running. Essentially you're running jobs over a single simulation will take many different computing jobs, and so you need to keep track of what's going on there. You need to keep track if if there's a problem that happened to the run, maybe you need to restart. Maybe some data was corrupted. So these are tools which allow you to basically set up these simulations. There's also another issue. Einstein Toolkit comes in the form of source code. You have to compile the code on the clusters that you're running. Well, Simulation Factory helps you there because people have worked out how to compile the code, how to set things up on many different clusters. That information is all stored in Simulation Factory. So if you're working on a known cluster, you can just use SimFactory to actually set things up for you. On the other hand, if you're working on a brand new cluster and you figure out how you need to run it, then you could add that information. You can add that support back into SimFactory, and other people can use it. I've mentioned Crank and NERPy. Those are code generation. Those are tools which generate code for you. So they basically they take some kind of tensorial expressions and turn them into actual C code that can then run on the toolkit. And there's also then many different codes, some generated with Crank and NERPy, which are actually used to actually do the science. So for example, if you want to solve a neutron star simulation, you want to solve a binary neutron star, a merging binary neutron star, you would need to have a code which can solve the magnetohydrodynamics associated with the matter. You would need a code that can solve for the spacetime, and they have to work together. And so there would be, there would be core science modules that you'd have to activate. Perhaps you might activate the McLaughlin code to solve the spacetime, and perhaps you might activate Illinois GRMHD to do the MHD. But even if you were doing a binary neutron star simulation, there'd be a bunch of other modules which you'd be activating. And I think you'll hear about various ones as the week goes on. Okay, the guiding principle is that it's community driven, it's open development, and then we need to have, and then good interfaces between, so we break the problem up, different modules handle different parts of a problem, and we have interfaces which allow the modules to interact with each other. Separation of physics from the computational infrastructure. You'll see as you get more used to the toolkit, it's much easier to write, straightforward to write a physics application, brand new physics application, than it is to actually handle all the details associated with the parallelization. So basically, as a user, you're mostly going to be writing a physics application, and you don't have to worry about all the details of actually handling the computation. Other principles is that it should always be production ready and high quality code. And high quality code means all the code that's released for the toolkit has been carefully reviewed and tested. Okay, and so the Einstein Toolkit itself grew out of the original Cactus code. So originally it was Cactus with some additional applications, and then the application, the number of features grew and grew, and then more features were added, and a lot of the features which people use as part of their Einstein Toolkit simulation are open source, but not all. You are free to develop your own code and keep it closed source if you so choose. Okay, so whoops, I jumped ahead. Let's talk about kind of the basic setup. So we have fundamental. Well, let's look at this as terms of the Einstein equations. So we have space-time curvature is related to matter. Okay, and so matter is, okay, hydrodynamics, electromagnetic radiation, scalar fields. And so physically, these are, we can imagine that we have different processes, very different processes going on between the left and the right-hand side of this equation. And so in the code, this split up is done through basically different interfaces. So there is this interface called ADM base, which basically handles interactions of the space-time. It doesn't do space-time evolution. It just handles how different codes which are going to be involved with the space-time evolution can interact with each other. Matter terms are going to be, their interface is T mu nu base. And because, let's say, for example, a space-time evolution code like MLBSSN requires access to the space-time metric, but also access to T mu nu, it's going to interface with both of them. Then a hydro code like GR Hydro, well, it's going to need to know about all the various hydrodynamic quantities, density, pressure, temperature, etc. And those quantities, the interface for those quantities is going to be in a interface in a thorn called hydrobase. But GR hydro itself is going to have to interact with hydrobase, T-mu base, because it's going to write quantities that the GR code is going to need. But it also has to interact with ADM base because it needs to know what the metric is doing. Okay, and then we have, well, additional things. We have initial data. So initial data generally consists of both initial data for the hydrodynamic quantities and the metric quantities. And we might have analysis, which again, would in general depend on both of those as well. And we can add more, then we can start to add more details. We can have more codes that can handle the GR case, more codes which can basically work with the hydro quantities. We can have scalar fields we can have scalar fields which will also interact through T-mu base. Okay. Okay, and one of the so we've talked about some of the guiding principles already. An important thing to recognize is that running a simulation might be relatively easy, but it is not. That's not necessarily where the science happens. There's a lot of physics required, a lot of physics knowledge required to actually set up a proper simulation and to basically extract the appropriate results from that. Okay. The Einstein Toolkit's job is not to teach you the science, but it is to make it so that you can use that science that you've learned and you can actually set up appropriate simulations. So if you're looking for help, for the science, then you should be, looking, for example, textbooks or consultation or working with other groups to understand the science. If you're trying to now that you know the science, you're trying to run a simulation, then the Einstein Toolkit will be there to help you for that. Okay, citations. The Einstein Toolkit is open source and free to use. As part of that, there's no requirements to actually cite anything. However, this is academia. You really should be citing. And so you're requested to cite, at the very least, minimally, there's a DOI associated with each Einstein Toolkit release. There's also a list of papers, and you can find that information on the Einstein Toolkit website. So if you're using particular codes in your Einstein Toolkit simulations, you can refer to that web page and to see exactly which papers the author has requested that you cite. Okay. The Einstein Toolkit is a living system. So new thorns are added on a regular basis with new features. So there's a new driver thorn called Carpet X, which has recently been added, and it supports calculations on accelerators as well as traditional CPUs. There are new GPU CPU codes available for the Einstein Toolkit. X is one. There are new spacetime codes. Spacetimes X is another. And so I've written these as upcoming releases. These codes are available, but they're not yet in the toolkit. So you could use them, but they have not yet gone through that rigorous testing that is required to actually be a code that's in the toolkit itself. There's a new algorithm for Carpet X that handles subcycling. If you worked with the Einstein Toolkit before, you may know about buffer zones, which is the way that carpet handles essentially AMR refinement boundaries. And it is somewhat, it suffers from the fact that it introduces a lower order accuracy error and an inefficiency due to increasing the number of points required. And so in Carpet X, there is a new algorithm for doing subcycling, which does not reduce the order of accuracy and doesn't require these extra buffer zones. And there are boundary thorns associated with the Carpet X release, new Rad X. If you're going to be using, if you're going to be looking at a Carpet X based code, you'll probably have to interact with a new Rad X boundary, which just handles the radiative boundary conditions. Okay. Other things, the Grail library is shown up in the Einstein Toolkit in various releases. Grail library. So Grail is again a code which is a library which is developed by Zach Edian's team, and it's a code which they have contributed to the toolkit, and it basically is a library to handle hydrodynamic GRMHD simulations. Another code from the same group is NERPy. NERPy is a Python-based code, and what it does is it can be used for, among other things, to generate a full evolution code thorn to be used with the toolkit based on again a relatively simple tensorial expressions which you can implement within Python. Okay. Other things I think we're going to hear about a little bit later today. CCE export. So there's been this very important new code which has been made available to the community from the Spectre group called Spectre CCE. This is a code which basically very efficiently takes data generated from a code like the Einstein Toolkit and incorporates and basically uses that to provide data for a subsequent evolution using what's called Cauchy characteristic extraction, which basically allows you to take the metric data at some relatively large radius and propagate it with very little error out to infinity to get the true waveform. And so CC export it's providing the interface between an Einstein Toolkit simulation and this Spectre CCE code. There's also I mentioned before, the FLRW solver, which provides initial data for cosmological simulations. Okay. So in summary, well, first things first is for the Einstein Toolkit, go check out the Einstein Toolkit webpage. It's very detailed and very thorough. The Einstein Toolkit provides tools for high-performance computing and numerical relativity. It's open source. It is an open community with researchers from around the world, and it's used in high-end research all around the world. Okay, and then just to conclude, it's currently supported by, it's been supported by these grants, both there are new grants there and some of the previous grants. And any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the National Science Foundation, which is just something we have to say anytime we acknowledged the fact that we've been supported by the National Science Foundation. Okay, I'd be happy to take questions.
Questions? So nobody's raising their hand, but I just, and this isn't really a question, this is sort of a comment, but one of the things that I just want to emphasize that we do in the Einstein Toolkit, right, is a lot of software projects, you get an initial paper and everybody cites the paper and then somebody else comes along and makes a contribution, and well, guess what? They don't get credit because they were never on that paper. That's one of the reasons why we moved to a DOI for citing the Einstein Toolkit, so that if you do make a contribution, any contribution, you can get added to that DOI. So if you contribute to the Einstein Toolkit, if you get the idea in your head that you want to write something for us and have it included, you can get credit. If you make a pull request to fix a bug, you can get credit. You know, if you just want to use our software to do your science and keep what you're doing secret, you can do that too. So there's a lot of capabilities here for collaboration and getting credit and being part of something. Yes, Johnny.
Say, you have a code that you want to incorporate into Einstein Toolkit. What's the process to do that?
So the question is, what's the process to get a code incorporated into the toolkit? And I guess since this is Yosef's talk, I should give you a chance to answer, or you can let me do it, whatever.
Steve, I'll be happy to defer to you.
Okay, well, the first thing I would recommend you do is you come on and talk to us on our weekly call, because we'll figure out all the details there. But generally, we're looking for high quality code. We want to see that you have a paper that you can demonstrate a community need, and then we have a code quality review that we need to go through to get you into our regular testing framework, and then it can be pushed out. So it's not a terrible process, but there is some work. There is some work in going through the steps, and we will be happy to help anyone through that who wants to do it. Any other questions? All right, well, I guess we've got about 15 minutes until the next talk. So if you haven't had enough coffee, there's probably a little more. All right, let's thank the speaker again. All right, see you in 15. Oh, there's a chat thing.
Yeah.
Does anybody know what the chat says? Oh, thanks. Okay. All right. Sometimes questions show up there, and